አባቴ ሲጠራኝ እያለ ና ቶሎ ምንም ሕፃን ብሆን ሚስጥሩ ባይገባኝ
Hello everyone, this is Q-Tutorial presenting you Grade 8 Mathematics. Grade 8 Mathematics contains 5 units. Unit 1, squares, square roots, cubes and cube roots. Unit 2, further on working with variables. Unit 3, linear equations and inequalities. Unit 4, similar figures. Unit 5, circles. In the first unit, we'll have 3 subtopics: the square of a number, the square root of a rational number, cubes and cube roots. The unit outcomes of the first unit are the following. So after completing this unit, you should be able to determine the square root of a number, determine the square root of a perfect square number, extract the approximate square roots of numbers by using numerical table, determine the cube of a number, extract the cube roots of perfect cubes. Coming to the first topic of the first unit, we'll be focusing on the square of a number, in particular the square of a rational number. Let's take our first definition. What do you mean by squaring the number? The process of multiplying a rational number by itself is called squaring the number or squaring the rational number. So when a number is squared, or a number which is found by squaring a natural number or a rational number, this number is called a square number. Square numbers in general, as the first square number is 1. Second natural number, as you know, is 2. 2 square is 4, so the second square number is 4. The third natural number is 3, and as 3 times 3 is 9, the third square number is 9. So what do you think is the 8th square number, for instance? Perfect. The 8th square number is 64, because 8 times 8 is 64. Now let us look at mathematical signs for square. To show that a number is squared, usually you put on a small 2 at the right top of a number, like the following: 2 squared, 3 squared, in general a squared. So here the number 2 as a superscript tells us that this number 2 is squared. The superscript 2 here tells us this 3 is squared. Here also in general, a squared with a superscript 2 tells us a is squared. So in general, 2 appears as a superscript or as a power of a number, and the number is said to be to the power of 2 or raised to the power of 2, or the number is said to be squared or the square of the number. Let's see some terms concerning squaring a number. If you take 25, the standard form of 25 is just this one, while 25 can be written as 5 to the power of 2. Hence here the base is 5, the exponent is 2. Together we have the power form of 25. There is a difference between a square and 2a. Here we need to note that there is a difference between a square and 2a. Let's try to take example to see the distinction between the two values. For example, if you take 4 square is 4 times 4, which is 16, but twice 4 is 8, and you can see the difference between 16 and 8. They are different. Take 31 square. 31 square is 961, while twice 31 is 62, and here also you can see a wide difference between the two numbers, 31 square and twice 31. But it doesn't mean that always it is true that a squared is different from 2a, because in case of 2 square is 4, at the same time 2 times 2 is 4. So in this case 2 square is not different from 2 times 2. So in most cases a square is different from 2a, but in the case of 2 and as well in the case of 0, a square can be equal to 2a. The square numbers and square figures. I think you can imagine that there is some relation between square numbers and square figures. Let us discover the relation. Take a figure which is 1 by 1, a square figure which is 1 by 1. Its area is 1 square unit. And now take a figure which is 2 unit by 2 unit. Its area is 4 square units. Now you see there are squares with a blue color and also a square, the previous square, with a red color. These blue color squares, the 3 blue color squares, were added up onto the 1 unit red color square to give us a 4 unit square figure. Let's see a 3 by 3 unit square figure which has an area of 9 square units. Now you can still observe that we have added 5 more squares onto the previous 4 squares to get 9 square unit figure. So 3, 5, when you take on the pattern or look at the pattern, it looks like the next unit of square units we are going to add up are going to be 7. So let's guess that. Yes. So when you add 7 square units onto 9 square units, it gives you the next square, which is a 16 square unit square figure. Okay, now you can easily predict that you need to add 9 square units on the previous square figure to get 25 square units. That is a 5 by 5 square unit. Therefore you can have a sequence of square numbers 1, 4, 9, 16 and so on and so forth, n square, and also the difference between consecutive square numbers forms a sequence of odd numbers 3, 5, 7, 9 and so on. The formula for that can be put as 2n plus 1, a perfect square table for whole numbers. Our observation is going to focus on the numbers between 1 and 99 inclusive. First of all, let's see how this table is constructed. You have row headers 0 up to 9 and column headers from 0 up to 9. This is different from an addition table or a multiplication table. This is simply a square table. In the row of 0, we will see the squares of the numbers from 0 up to 9. So in the first cell of the row of 0, you can see 0, which is 0 squared. Under 1, column 1, row 0, you can see 1, which is 1 squared, 2 squared, 3 squared, and so on, up to 9 squared, which is in the row of 0 and column of 9. We can consider these numbers as 0, 1, 0, 2, 0, 3, and so on squared. Okay? Now comes a very important way of reading. Take row header 1 with a column header 0 gives us a cell 1, 0, which is 10 squared, which is 100. Likewise, you have a row header 1 with a column header 1. Together it gives us 11 square. You read row header 1 with the column header 1, 11 square, which is 121. This is how you read. If you want to read, say, 19 square, you take row header 1 all the way to column header 1. So the junction gives us 361, which is 19 square. Okay, so you can easily read this table, square table, just by taking one row header and one number as a column header. You join them, then the square will be on the intersection column. So for instance, here 15 55 square. So you get it here, 55 square. Here is 55 square is 3025, right? Now a little bit more observation. In the column of 0 there are square numbers, definitely, that end up in 2 zeros, except these 2 zeros, but the hundredths digit and the thousand digits are like that of the digits in the first row. Here 1 square, 4 square, ignoring the 2 zeros, 1 square, 2 square, 3 square, 4 square, and so on. And here you have 81, 9 square. Okay, but just for observation, those numbers in the column of 0, the perfect squares in the column of 0, their last digits are 2 zeros. The perfect squares in the column of 1 have a last digit 1. Do you have another column that has got last digit 1, perfect squares? Yes, 9. 9 is another column that has perfect squares with a last digit 1. So 1 or 9, then the perfect squares in column 1 and 9 end up in digit 1, or their units digit is 1. Similar to those numbers in the column of 2 and in the column of 8 as well. So those perfect squares in the column of 2 have last digit 4, and those in the column of 8 are also have last digit 4. This similarity is also true to the column of 3 and 7. They have a last digit 9. Their last digit is 9. Those numbers in the column of 3 and that of 9, they end up in the last digit 9. Again, in the column of 4 and 6, you see similar, you have a similar observation, but this time you have the numbers ending in 6. But those numbers in the column of 5, they end up in 2 digits, in 25. That is a nice observation, will lead you to a very important guess. Now let us focus on these relations. Focusing on these relations, say in the middle column, in the column of 5, we want to have more observation. To determine the numbers in the column of 5 as a whole, we can have 2 ways. One is a general method, another is a particular method for the column. For the general method, consider 15. Okay, 15 square. It has units digits 5 and tens digit 1. Follow me how we are going to calculate 15 square. Alright, if you memorize it, that's nice, but without memorizing, there is a way of calculating 15 square as follows. First you take the tens digit square, which is 1 square. Okay, 1 square here. Now take twice the tens digit square and times the units digits, twice the tens digit, which is 1, times the units digit. Lastly, you take the unit digit square. Alright, the tens digit square is 1 square, which is 1, twice the tens digit times the unit digits is 10, 2 times 1 times 5, and the unit digits square is 25. Okay, so what are we going to do? First, take from the unit digit square here the unit digit, which is 5, and put it here. Again, take the tens digits of the unit digit square, that's 2 as a carry, to 10, twice the unit digit times the tens digit. So together that gives us 12, and take the unit digit of this 12 to that place here. Until now we have 25. Lastly, you add up 1 onto 1 as a carry, and you get 2 and take it there. So together it gives you 225. Okay, 225. Similarly, now we can calculate 75 square. So what are we going to do? You take 7 square twice the tens digit times the units digit, 2 times 7 times 5, and the units digit square, 5 square. Then what that gives us 49 for the units the tens digit square, 7t twice the units digit times the tens digit, and 5 square, 25. Okay, so from here first you take the unit digit 5 here, then take 2 as a carry, that gives you 72, and then write 2 here. Until now I have written 2 and 5, and then the remaining 7 taken as a carry to 49. Okay, then remaining 7 taken as a carry to 49, then gives us 56, and the whole 56 is brought here. Now the whole thing is 5625. So 75 square is simply 5625. The other way to calculate for the numbers in the column of 5 is as follows. Now I will demonstrate it by using the previous numbers 15 and 75 as well. So what you do is, 15 is found in the first row, right? It is a number in the first row. Mind you, the first row numbers are 10 square, 11 square, up to 19 square, so 15 exists in the first row. So that is a row number. You take the row number 1 times row number 1 times row number 1 plus row number 1 plus 1, which is 2. So 1 times 2 times 10, times 100 plus 25, that gives you 225. Okay, 225. So that's exactly what we had in the previous case. 15 square is 225. So row number times 1 plus the row number, the row header, times 100, it gives you plus 25, gives you 225. Similarly, for 75 square, we can proceed in a similar fashion. 75 square, you find it in the 7th row, or in the row headed by 7, and the row plus 8, plus 1 is 8, so 7 times 8 times 100 plus 25, that is 7 times 8 is 56, times 100, 5600 plus 25, 5625. Okay, so that's an easy way to find the numbers in the column of 5. So from the previous table we have observations that the numbers in the column of 0 end up in 2 zeros. The numbers in the column of 0 end up in 2 zeros. The numbers in the column of 1 or 9, they end up, their last digit is 1. The numbers in the column of 2 or 8, their last digit is 4. The numbers in the column of 3 or 7, their last digit is 9. The numbers in the column of 4 or 6, their last digit is 6. The numbers in the column of 5, their last digit, they end up in 25. Okay, this is a very important observation. We have it previously, we are trying to use this relation very well. So here are examples. You want to find, using the above relations, use the above observation to find the numbers whose squares are 7,921, 5,041, and so on, up to 8,649. Okay, so what square gives us 7,921? Let's see. Now let's go to the solution. Consider 7,921. 7,921, you find it in the 8th row, because 79 deleting 21, you get 79, and 79 is a number between the two squares. That means 8 squared 64 and 9 squared 81, so it exists between 64 and 81, so it is in the row of 8. It exists in the row of 8. Now it remains in what column, to determine in what column this number belongs to, which is either, as it ends in 1, the last digit of the perfect square is 1, then either it is in column 1 as in the previous discussion, or in column 9. To know whether the number is in column 1 or 9, we have a test here. If the number, which is 79, found after deletion of 21 here, is more than 8 times 9, which is the row header 8 times row header plus 1, 9, 72. 79 obviously is greater than 72, which means as it is greater, you take the larger number 9. So what happens is, first you take 8 for the row, next you take 9 for the column, the number belongs, which means 7,921 belongs to. So 7,921 is 89 squared. So the number to be squared is 89. Likewise, taking 5,041, this number, when you delete 41, you get 50. This 50 is between 49 and 64, so 50 is obviously in the row of 7. And as this perfect number ends in the digit 1, it still belongs either to 1, column of 1, or to a column of 9. To determine that it belongs to a column of 1 or 9, we compare with 7 times 8. What is 7? The row that 50 exists the same, and 8 is row plus 1. So if 50 is less than 7 times 8, which is 56, then meaning this number 5,041 exists in the column of 1. So when it is less, in the first column, when it is greater, it is in the next column, right? So as in the previous, in the 7th row implies you put here 7, and in the first column you put here 1, together it gives you 71, meaning 71 squared gives you 5,041. Let's go also, let's consider 2,704. In the case of 2,704, You see, the last digit is 4. The last digit of this number is 4, meaning either this number exists in the column of 2 or 8. The row this number exists in, by deleting 0, 4, you get 27, and 27 is between 25 and 36, the two perfect squares, consecutive perfect squares. So 27 is in the row of 5, 2704 is in the row of 5, then either in the column of 2 or in the column of 8. Then we determine this by considering the test. Take 5 times 6, row plus row times row plus 1. So 5 times 6 is equal to 30. When it is compared to 27, 27 is less than 30. Hence, you take the lesser number. Thus, the number is to be squared is 52. Now, let us take 3,364. In the case of 3,364, still the last digit is here is 4. The number exists in the column of in the row of 5. As it ends in 4, either it exists in the column of 2 or 8, but we want to determine whether it belongs to the column of 2 or 8, because that is very important, because as it exists in the row 5, we take 5 first, the tens digit becomes 5, and now we want to determine the units digit, is it 2 or 8? Okay, by deleting 64 from here, take 33, compare it with 5 times 6, row header times row header plus 1. When you compare it, 33 is more than 30, meaning you take the largest or the larger number, which is 8. So 58 is to be squared to give us 3,364. Let's go on. Let us take 4,489. This number exists in the 6th row because this number is greater than 36 and less than 49. Okay, I mean 44 is greater than 36 is less than 49. When you delete 89, you get that number. Okay, so it is in the 6th unit, in the 6th row. So you take here 6 as in the 10th place. Now it remains to determine the units place. Is it 3 or 7? You compare 44 here with 6 times 7, which is 42, as 44 is greater than 42. You take the largest number, or the larger number is 7, so 67 is the number to be squared to give us 4,489. Now let us take the last one. The number ends delete 49, take 86. 86 is between 81 and 100. The number exists in the row of 9. It exists in the row of 9, and as it exists in the row of 9, you take 9 first here. The 10th digit becomes 9. Now it remains to determine the units digit. Is it 3 or 7? Because the last digit of the number is 9. Either it belongs to a column of 3 or it belongs to a column of 7. You take 86. 86 is less than the row header, 9 times 1 plus the row header, 10, 90. You take 3 as a units digit together, that makes 93. So that's all. Now let's take rational numbers here. It's very important to look at also rational numbers. If our rational number is half, then 1 over 2 squared is 1 over 2 times 1 over 2, which is 1 over 4. Similarly, if you have given just a decimal number, 0.19, then when you want to square it, it's better to write it into a fraction form. 0.19 is, first of all, can be written 19 over 100 square, and 19 over 100 times 19 over 100 is obviously 19 times 19 is 361 over 10,000. And finally it gives you 0.0361. Okay, now let's take exercise. Here let us determine whether each of the following statements is true or false. Take 15 square. Is it equal to 15 times 15? Obviously, yes, true. Take 20 square. Is it 20 times 20? True. 19 square. Is it 19 times 19? True. 81 square. Is it twice 81? No, false. 41 times 41. Is it equal to 41 squared? No doubt. True. Negative 50 square. Mind you here, negative is out of the bracket, hence it should have been like negative 2500, but here you have only 2500 positive, so this is false. X square, is it equal to 2x? No, not necessarily, but by chance if you take say 2, yeah, it is right. But take several numbers, like if you take say 1 square is 1, but 2 raised to 1 is 2, so 1 is different from 2. One nullifying factor when the statement is false. S square is equal to 2 raised to 2x, and now that's false. Negative 60 square. Oh, this time just compare negative 60 square with negative but 15 square, but these are different, and here the negative sign is within the brace, so when this is squared, definitely it gives us positive 3600. It's like 60 square, so true. I is true. Find the square of each of the following. Obviously 8 square 64, 12 square, it has to be automatic, 144, 100, 444. 19 square, well, if you only know the numbers from 1 up to 9, their squares, then you need to have a means of determining 19 square. This time we may introduce one little bit very important trick. 20 square, you know, it is 400, but 20 minus 1, you know, it is 19. Then we want to use this relation. For that matter, just let's look at this formula. N minus 1 times n minus 1, you know, it is n square minus 2n plus 1, okay, which is n square plus 1 minus 2n. It's helpful. N plus 1 times n plus 1 is n square plus 2n plus 1. Okay, so now let's use this in finding 19 square, which is 20 minus 1 times 20 minus 1. 20 times 20, which is n square 400 minus 2 times 20, 40 plus 1. Obviously 401 minus 40, which is 361. Likewise 51 square, okay, it is 50 plus 1 times 50 plus 1. By this formula it is 50 square 2500 plus 2 times 50 plus 1. Altogether makes 2601. 63 square, right? It is as in the previous case, if you remember, it is 60 plus 3 the whole square. 60 square is 3600 plus 2 times 60 times 3 plus 9, which is 3 square. So that gives us 3969. Here the number should have been 16. Okay, now the other way to work on 63 square is
you take 6 square, the 10th digit square, as in the previous, twice the 10th digit times the units digit, again the units digit square. Okay, first of all you take the units digit, the unit digit square units digit, that's 9 because it is 9 only, and so first you take 9 from the units digit, then you go to twice the 10th digit times 3, which is 36. Okay, from it you take 6. Okay, then take 3 as a carry and add it up onto 36, becomes 39. Okay, so altogether 3969. 100 square, you must know this is 10,000. Find S square in each of the following. Well, as in the previous, we may be focusing on say like 1 over 6 square. 1 over 6 square is 1 over 6 times 1 over 6, which is 1 over 36. 0.3 square, you can write is negative 3 over 10 times negative 3 over 10, which is 9 over 100, but this time positive. So 9 over 100 is 0.09. Okay, you can also multiply it as it is now. Negative 20 square, as in the previous, which is positive 100. Negative 50 over 3 square, it's like negative 50 over 3 times negative 50 over 3, 2500 over 9. Take 50 square, 56 times 56, but you can use the previous technique. 56 square is like taking the 10th digit, it is 5 square, 25, 2 times the 10th digit times the units digit, 5 times 6 is 30 times 2, 60, and then the units digit square 36. Now from that take the units digit 6 and carry 3 onto 60, which is 63. Take 3 again, carry 6 onto 25. 25 plus 6 is 31. Altogether 3136. Well, 0.07 square means 0.07 times 0.07, which is 7 over 100 times 7 over 100, 49 over 10,000. And then when you change it into decimal form, it becomes 0.0049. Find two square numbers which are to give a square number. The obvious square numbers that give us another square number are 9 and 16, because 9 is a square number and 16 is a square number. The sum of the two is 25. Okay, there is another square, there are other square numbers that have similar property. If you take 4 times 9 and 4 times 16, which are 36 and 64, these numbers also add up to another square number, which is 100, because they themselves are square numbers. So the easy thing to do is a square number multiple of 9 and 16 also adds up to simply to a square number. Okay, we don't have fixed square numbers. For instance, if you take 9 times 9, that is 81. 9 times 16 is 141, which gives us 225, another square number. Okay, well, we don't have simply two square numbers, but we have several of them. From the list given below, indicate all numbers that are perfect squares. Now it's time for us just to make some practice concerning perfect squares here. And obviously 50 is not a perfect square, 20 is not a perfect square. Had these numbers been perfect squares, they should have ended in 2 zeros. 64 is a perfect square, which is 8 square. 30 is not. 1 is a perfect square. 80 is not. 8 is not. 49, yes, it is a perfect square. And 9 is a perfect square. Here 10 is not a perfect square, 21 is not, 57 is not, 4, yes, is a perfect square. 60 is not, 125 is not, 16 is a perfect square, 27 is not, 25 is a perfect square. C, from 137 is not, 150 is not, 75 is not, 110 is not, 40 is not, 625, yes, it is a perfect square. 64 is a perfect square. 81 is a perfect square. Oh, consecutively these are perfect squares. 144 is also a perfect square. Take 90 is not a perfect square. 180 is not. 216 is not a perfect square. 81 is. 169 is a perfect square. Show that the difference between any two consecutive square numbers is an odd number. Previously, with the help of figure, we will be able to determine this is true. That means the difference between two consecutive perfect squares is odd number. Now let's just check this by using arbitrary number. Consider an arbitrary natural number n, and n plus 1 will be the next natural number. So the squares of this n square and n plus 1 square gives us perfect square. N square and n plus 1 square will be consecutive square numbers. Now n plus 1 square minus n square is n square plus 2n plus 1 minus n square. Then this becomes 2n plus 1, which is the previous formula. N square cancelled with n square, then what remains is 2n plus 1, which is the formula for odd numbers. Just if you give it 1, it becomes 3. The second difference is 5, and so on and so forth. The other question is, it says show that the difference between the 7th square number and the 4th square number is a multiple of 3. First of all, you take the 7th square number and the 4th square number. The 7th square number is 7 square, the 4th square number is 4 square. The difference is 7 square minus 4 square. Okay, this is the difference of two squares. It's written as 7 minus 4 times 7 plus 4. Okay, and this is 3 times 7 plus 4, meaning 7 minus 4 is 3. So 3 times 7 plus 4, 3 times 7 plus 4 implies that the difference of the 7th square and of that of 4th square is a multiple of 3, whatever here you have. Thank you.